So good afternoon, everyone. Thank you very much for joining this new session of the Urban Model Seminar, the sixth one. I'm Clémentine Cotineau, and together with my colleague Ruta today, she can wave, we're happy to see you again for discussing analytical urban models and their circulation. Once a month, we receive an expert or two experts in this case of urban studies and urban modeling to dissect one model with a general question in mind. And this question is always the same. It's what are the unforeseen consequences of urban model simplifications on our understanding of cities? So we're starting from the premise that urban models are simplifications of reality, but simplifications which also translate modeling choices, implicit or explicit, and therefore they have consequences on how we view, how we represent, and how we act on cities. So we're trying to trace back the discrepancy between model results and empirical analysis back to the urban model's core assumptions and design choices, with the aim of providing guidance on how to use classical urban models appropriately, to avoid misleading conclusions, and ultimately to create better urban models. Last month, we have received Ron Boschma to talk about the unforeseen consequences of evolutionary economic geography and the concept of relatedness. If you're interested in his talk, it's available now on our YouTube channel called Urban Models Seminar. You can see a representation of this YouTube channel. Today, I'm very happy to introduce two speakers. So we've got Itzhak Benenson Erez Hatna to talk about the famous Schelling model of segregation. So Itzhak Benenson is full professor, head of the Geosimulation and Spatial Analysis Laboratory at Tel Aviv University, Department of Geography and Human Environment. The areas of his academic expertise and interest include geosimulation, spatial analysis of urban and regional phenomena, modeling of urban residential dynamics, long-term impact of local and regional plans, public transport and parking in the city, vehicle-pedestrian interactions, and spatial big data analysis. Erez Hatna is a clinical associate professor of epidemiology at NYU School of Global Public Health. He works in the fields of geoinformatics, spatial analysis, and agent-based modeling. He studies urban dynamics, residential segregation, scaling laws of urban systems, and infectious disease modeling. At NYU, he's part of the agent-based modeling lab, which works with large-scale epidemic models and cognitively plausible agents in order to produce a transformative synthesis of global public health modeling. Today, they will focus on a topic that they've collaborated on together quite a lot, which is presenting the Schelling model, but also its impact on how segregation is approached, both in urban studies and in urban planning. So they'll be reflecting on the simplicity, but also the limitations of the Schelling model and the reasons behind its wide circulation, as well as its
No, we lost Clementine.
Yeah, unfortunately.
So then I would just suggest you to start, and yes, I stopped sharing, and I think we will soon get Clementine back. She has almost finished with the presentation, so we're fine.
Okay. So let's start. I don't know what is the state of your screen. On my screen, Clementine is the first, then myself, then Erez. So I believe you see both of us somewhere on the top of the list.
Yeah.
So we will actually exchange during the lecture twice. Each of us will talk twice. I will be the first, then Erez, then myself, then Erez, and maybe I will make some final couple of final slides. I don't remember actually. So that means I will share the presentation and Erez will tell me next and next and next when his turn will come. Okay. And we are really happy that you joined this lecture because the state of mind of many of us these days are like with that Russian aggression in Ukraine. Some people lost the ability to work. And they're talking about the news all the time. So thank you for joining. let's put it aside for an hour and a half and enjoy Schelling model and that very nice and very aesthetic stuff that is related to this model. So I'm trying to share my screen properly. Okay. And because we are two, so I'm asking Erez, is it okay with the presentation?
Excellent, beautiful, thank you.
Okay. So this is the title. And this is the content. The presentation consists of 4 parts. You see them written. It's the advantage of Zoom. I will not read that. So the history, I will start with the history. The history is presented in all these details in the paper. I will cite in a couple of slides. The Schelling model was actually invented by 2 people. And you know, all of you know this model, what this model is about. So it's just a brief reminder. But I will show, sorry, I have to hide floating controls. Okay. So 2 inventors, James Sakoda and Thomas Schelling. And I think most of you remember that James Sakoda actually was the first who invented the idea that interaction between individuals of different properties can lead to segregation of groups, can lead to segregated spatial patterns. It was very long ago. It was the time I think none of the participants was born. It was in 1949. And this is, let's say, the metaphor of his model, and very similar metaphor was invented in 20 years by Thomas Schelling. We don't know whether Schelling knew about Sakoda or did not know about that. It doesn't matter much. They have very different sources of inspiration. The source of Sakoda inspiration, I wouldn't say it was that positive. It was his young youth in a segregation center that was a washed name for the camp for Japanese in the United States during the World War II. He moved from one to the other. He was first in some Tule Lake segregation center. He was decided to be a loyal member of the American society and was moved to some mini Docker relocation center for almost 2 years. Together with his family, he has brother and sister as far as I remember. The source of inspiration of Schelling was actually residential pattern, which was segregated in the United States at that time. Definitely, they don't have these nice maps people have constructed very recently, but people knew about segregation, so that was the reason of Schelling, as he writes in his book. And here below, you see the reference to that paper of Rainer Hexelmann. It's a huge paper of more than 100 paper, very interesting one, very nice reading. I really recommend it, where he describes the historical development of these 2 people and these 2 models and the interaction between them. In a couple of minutes that we have for this historical reminiscence, I will point to 2 different formal sides of these 2 models. As you can read on the side of Sakoda, and the title of his PhD thesis recalls that he was in that center at the second one. So the idea of his model is a little bit different from the idea of Schelling and the general view as we get used to that view of the model, as we get used let's say last 30, 40 years. So I would say that Sakoda model is more sociological than the model of Schelling. Schelling is a more kind of physicist when he considered the population distribution. Sakoda talked about interaction between individuals. Formally, it comes with the movements the agents of Sakoda can make on the checkerboard. They can move one cell any side and size, and they want to be closer to the people they prefer and to be farther away from those they don't like. So every step is only one spatial step to adjacent cell, and then the person decides whether it's good or not. And actually the person decides, as it's written here, beforehand, whether to approach or do not other people. Schelling looks in terms, I would say, mean field theory. You observe what's around, and if you don't like it, you relocate. Initially, Schelling model, I think it's graphically presented here. So this is Sakoda one. So these are individuals that move. And every move, when you approach or you go farther away from the other, gets some estimate. You change, let's call it, we will call it later, your utility by those moves. So by playing with the utilities, which are expressed by those 2, 2, 2 matrices on the top of every example, you can generate whatever you like. And people from time to time get back to Sakoda model and try to understand at what extent all those weights expressed here reflect something, whether it's something more than now it's computer game, or it's something that reflects our social attitude to each other. Most of the people followed the line of Schelling. The initial version of the model was one-dimensional, and that was, but in that specific version, it was also stated that the major assumption of the model is to react on the fraction of friends nearby. What is nearby can be defined in different ways, but the major issue is that you observe the neighborhood, you estimate the fraction of friends. It doesn't matter whether the friend is located inside the neighborhood. And if this fraction is not high enough, this fraction is always denoted as F capital. So if this F capital is not high enough, you want to relocate. How to relocate is also, let's call it the qualitative parameter. In the first version, you could relocate another place and squeeze between other agents. So the space, the structure of space was not constant, it could change. In a year, Schelling published another version of his model, two-dimensional version. Again, I have to close the controls. Okay. And it was close to what we get used to see later when people start presenting Schelling model. It was sparsely populated board, 10 to 10 board, with I don't know how to call this symbol. It's only Hebrew in my head.
Asterisk.
Hashtag?
Asterisk.
No, no.
It's not asterisk.
No,
Asterisk.
number.
Number and zeros. So he was, even those years, he was politically correct. So numbers and zeros. And you see that the occupation is at the level of 70%, 75%. And the only rule was if there are more than 1/3, less than 1/3 of friends, move. And when you play with the checkers on the board, you immediately get segregated patterns, which depend greatly on initial distribution of numbers and zeros. And that was the result. The major result was that 1/3 of F is enough to get a segregated pattern. And it was at that time, and still remains, I would say, a little bit counterintuitive. The intuition, my primitive intuition says it should be a half. If there is less than half, I'm not happy, I'm moving, I generate segregation. No, it's much less. 1/3 is much less than a half. And that was actually the extraction of the very basic fact of the dynamics of spatial patterns, which are self-organizing. That was the reason, I would say for myself, that was the version of Schelling that occupied our minds in the beginning of 70s and not the version of Sakoda. A very clarified model with actually one parameter and counterintuitive consequence, the result, which as it turned to be is extremely robust. I think that's the end of the historical introduction. To make this lecture less boring, if you have questions, it's a good moment to ask. So please go ahead. Zoom lectures are usually boring. So let's interrupt we were asking to interrupt and to ask something. Go ahead. Okay, Gata, please go ahead, but unmute yourself.
Yes, thank you. Yeah, I have a question about the Sakoda model. Can you hear me?
Yeah, indeed.
Okay. I have a question because you mentioned that it was based on the sensitivity to the kind of interaction, but then how did it work? Was it that when people had interactions with each other, and they were nice to each other, then they wouldn't move?
Yes, indeed. They could be nice to each other. They could become enemies. So that small table 2 to 2, the coefficients, they can be positive and negative, and an absolute value was also important. So in this way, you can generate whatever you like. And the issue becomes, what is the meaning of those coefficients? And we see now, after many years, that the question was too complicated. So you immediately enter the multi-dimensional space of parameters where you don't have sufficient intuition. It's the problem of sociological models. They should be intuitive. You always want to put it in front of the reality and say, okay, it reflects something. So it was too much. Schelling was very simple, and that was a great advantage.
So that there weren't any, in the Sakoda models, there weren't any categories like men, women, or young, old people, but only the interactions.
Only interaction, but you could make your interpretation, but it wasn't called by those names. Yes. Ruta, please go ahead.
Yes, thanks. Because there was linear and two-dimensional model, and I think first the linear model was created, and then the two-dimensional model was elaborated, was more complex. So can we forget about the linear model because it was just the first step, or is it still relevant?
There is, I would say, analytical solution for a linear model. So the issue is more or less closed. Somehow it's intuitively, it's not realistic enough. So if you get to that model, it's an internal controversial. I will never tell it properly. So it's a kind of controversial for yourself. You can make simulation. You can try to write formulas. You know that someone wrote a paper, which is a mathematical paper, which is quite complicated. The statement in the paper is, I've resolved everything about this model. So either you have to read that paper and agree or disagree with the other, or you have to make your simulation with the danger that it's already resolved theoretically. And there is also a problem of space representation. So it should be kind of a circle, right? On the circle, the case of a distance becomes complicated. What is the distance here? That's the reason that people don't investigate it that much. So there were, let's say, several papers, then that theoretical solution, and there is no more attention to it, I would say. Okay, Erez, please go.
Okay, let's move forward.
Yep.
Yes. Okay, so let's talk about the settings of this model. We're going to use this setting. You can see a grid of cells. We have blue agents, green agents. We can represent racial groups, ethnic groups, or whatever we would like to represent. And we're going to have also empty cells, white cells. And agent can move to empty cells. Can you go to the next, please? So again, we need to define what is nearby. What does it mean? What is the neighborhood? What is the local environment of an agent? There are many ways to define it, really. A very common way is to define a Moore neighborhood of different sizes. A 3 by 3 is quite common, 5 by 5. And as we're going to see in a moment, the choice of the neighborhood can be important and also have some advantages. So usually we don't like to use small neighborhoods. Something intermediate is actually usually preferred. Also, when we use this model, we have to define to say, would we like to have boundary effects or not? Usually people don't like to have boundary effects, So they're using like a torus configuration instead of, however, in some cases, boundary effects are interesting and people actually use a regular plain grid. Next, please. So we have the tolerance threshold. This is the main parameter. It means that what is the proportion of friends that a person would be happy with. So let's say I'm an agent. Let's say that in that case, all agents in our models usually would like to have the same proportion usually. So maybe agents would like to have 75% of friends like them. So I look around. If I have 75% of more of people like me, I'm happy. If I have less, I'm unhappy, and I'm trying to move to a place where I'm going to be happy. So usually it's about being happy and unhappy according to, do I have enough friends around me? And usually enough friend is a proportion between 0 to 1. And in this case, we have an example. You can see like two clusters of green and blue agents. Let's say, for example, that the agent of the boundary would like to have 75% of friends, people of the same color. So they might move inside the cluster and then they will be happy. So it's all about moving from an unhappy place to a happy place when you have enough friends. Next, please. So here we have an example of what is going on again. So we have an agent, he's marked in the middle, and let's say that he would like to have 50% of blue agent. He's blue, so you'd like to have blue agents nearby, but he doesn't have blue 50%. So, okay, he might be able to find a place when you have a 50% of more friends, and then it becomes happy. So you see how simple the model is to understand, and it has this kind of very intuitive. It's one sentence. The model itself originally is simply not a model; it's actually a description. And there's a lot of detail to fill. So now we're going to start to fill the details. And of course, different people can fill them differently. But we're going to take the approach which is usually used. Can we go to the next one, please? Okay, so as I said, person actually calculate the proportion of friends in their neighborhood. The neighborhood itself is discrete. It's a subset of cells. So our parameter is not continuous. We actually have a finite set of values which we can use. For example, if you have a 3 by 3 neighborhood, you only have 23 unique fractions to investigate. So a parameter has 23 values. If we use a 5 by 5 neighborhood, we have almost 200 values. So this is one reason why sometimes we prefer to go to a larger neighborhoods, because now we have more values of the parameter to sample, and we can look more carefully and get a more detailed picture of the model. Please, next. And now the settings. Now, there are many ways to initialize the model. In our case today, we're going to focus on random initial configuration, where agents are randomly situated in space. We're going to focus on high density of agents. So only 5% of the cells are going to be empty. 95% or more are going to be occupied. Why? Because we prefer here to focus on urban scenario where in a dense city. However, if you would like to model a rural area, of course, you can use lower lower densities. However, you might need to do to change the model a bit. Also, we're going to play with the proportional of blue and green agents. And in general, agents are going to be randomized in order. So each agent would have one opportunity to move at each time step. And the order is going to be random. And also, we're not going to define what a time step means in this case. So it's a month, a year. We're going to ignore the meaning of time. Next, please. Now, in general, when we're going to talk about the model, we need to define a utility function to how people evaluate the neighborhood. The most simple one, which I just told you, is the binary one. If I don't have enough friends, I'm unhappy. If I have enough friends, I'm happy. It's a binary utility function. You can see it in the upper left. Other ones also come to mind, like for example, that there's a degree of happiness. I can be more happy, less happy, until I'm becoming really happy. And we're going to play with these two scenarios next. But you can also have many functions. Some can have a local maximum, and your results are going to be actually dependent on this. Next, please. Now, when we run the model, of course, the first thing is to look and eyeball the results. Look at run the model, get to some kind of equilibrium, and then, like an artist, say, this is look segregated, this look integrated. However, we also need to measure automatically or consistently the pattern, and there are many ways to do it. In this lecture, we're going to use a Moran-I autocorrelation index, and it's simply going to be every pattern would be a standard number. When the number is low, close to 0, it means that we have something like close to random pattern. If you have a high number, close to 1, we have a segregated pattern. In the middle, we can get some intermediate configurations. So we're going to use the model I simply to measure the level of segregation. There are the options, of course. This is good also for continuous variables. However, if you have multi-categorical variables, be careful about using this approach. Next, please. So here we have an example of a few model runs, equilibrium patterns. We started from a random pattern. We run the model. Now, if you can see here to the left, you see the utility function. I'm happy if I have enough friends. I'm unhappy if I don't have enough friends. So you can see that when I'm completely tolerant, f equals 0, nothing happens. Now, when we increase the tolerance, I become more biased. Then segregation starts to emerge. Unfortunately, this function has some problems with it. When I'm very intolerant, I would like to have many friends. I become very picky. Like I have my dream apartment. I'm unhappy in my position, but I would not move if I won't find my dream apartment. And it doesn't be realistic because sometimes people tend to to improve the situation. They tend to compromise. Maybe I can't find my dream apartment now, but I can go to something better. In this approach, actually, this is not possible. If we go to the next slide, we're going to see that when an agent would like to have 75% of friends, nobody moves because they're so picky. They say, unless I find my dream apartment, I would not move. And then what happens is all agents are practically unhappy and they're all suffering. And it's not nice for them to suffer, of course. We want them to be happy. And it doesn't really make sense from reality, because we know that if people don't like to be near each other, they're going to find a way to get away from one another. So usually we are creating a modified utility functions, like the one we're going to see next. And here we consider the following. You know what? Agents can actually improve the situation. They can actually the closer you are to your dream apartment, the happier you are. Of course, you're only completely happy when you have enough friends, more than F friends in fraction. But of course, the closer you are to your dream, to your utility of one, the better you are, and you're willing to climb the ladder of life stage by stage, and hopefully in a few years you're going to get to your perfect location. Also, the Schelling model does not include everything. Actually, it includes almost nothing in a way, because it's only one part, one component. So it's good to add some random movements, which represent other factors which we are not really representing. In our model, we're going to say that if you are happy, if an agent is happy, he might move to another good location. In other words, if you are happy, there might be other reasons for you to move that we are not really going to incorporate in the model directly. And in this way, we are avoiding a situation where the model stalls, is stuck in some suboptimal situation. Next, please. And here you see the result when you're using the modified utility function. And this is, I think, the classic result of the Schelling model. You can see that this is almost a tipping point. When agents, for example, would like more than 21 or 25% agents, when people say, as long as I have 20 or more percent of agents like me, we get integration. They are not forming clusters. But when we are about 21%, we get a very high level of segregation and almost nothing in the middle. And you can see the Moran I index jumping immediately from integration to segregation. And in the middle, it is like F5/24. You can see that it's still segregation, but with a fuzzy boundary. Let's go to the next slide. Let's look at a run of this situation. You're just on the tipping point. So segregation is really forming really slowly. So you can see a cluster are growing very sluggishly, but it's very small. Over time, the boundaries are going to be straightened up. So you got the system is going to minimize the interactions between agents, because a straight line is going to minimize the interaction between two groups. However, you can see that it is a fuzzy area, and it's not a very clear boundary. Actually, quite nice result. However, it happens only for one of the parameter values. Here you see, now we have equilibrium. In a way, it's going to change, it's going to be modified, but statistically, we're going to get the same I all the time, more or less. Can we continue, please?
Okay.
And just to a few words is that our model is really different than the standard Schelling model, which is simply a story. So in a way, we say we have some random movements of happy agents. This way, the system can move to a higher utility state. Also, notice that we actually considering all the area as one market in a way. There's no distance decay. You can jump from one area to another with no cost. Of course, there's no cost of movement. You can move it every time step if you would like to do so. And also, we see that every utility function that people actually can improve the situation, and they can move to better places, even though it's not their dream location. And now I'm moving back to Benenson, I think. See.
Okay, thank you, Erez. Actually, it's a time for question, because we continue with the extensions of Schelling model. What I want to add one sentence to what Erez has presented. The set of rules that he presented in these simulations is the minimal set of rules that produces the intuitive results. So again, I want to repeat, what are these two additional components that was specified in Erez presentation. The first is probability to move without a reason. It's actually a low probability. You don't have to make it 20%. 1% is enough. The second is the tendency to improve your situation despite not to be able to become happy. So you evidently can vary everything, but when you will start to vary that, you will always get something which is counterintuitive in a bad sense, not in a sense of Schelling. That's my addition, but please go ahead with the questions.
Yes, please, Clementine.
Yes, thank you. I had a question, so Itzhak answered it a little bit for now, but I was wondering exactly about, you showed two ways of augmenting the Schelling model to make it a little bit more realistic, but there are a million avenues to do that, and especially on the spatial side. So for example, for me, what's always jumped at me as so unrealistic is the homogeneous distribution, like one square. And typically for a city, because it's usually used for city segregation, we've got the effect of density and the fact that, well, people are one on top of each other and things like this. So I was wondering about, yeah, the priority of the rules that you introduced, and is there a hierarchy of the rules that need to be introduced first in a Schelling model, according to you?
Well, I think yes, because all the stuff you described are really important, and they were partly studied. However, we are trying to put something minimal and consistent with the basic idea. For example, putting more than one agent on top of each other actually is an extension. It's a relaxation. Now, don't forget that it not be vital, because when the model is statistical, every agent is doing the statistics of his environment. So when you put agents on top of each other, you're doing the same thing. What you're doing, you're actually imposing the neighborhood on top of each other. So it's actually not that different. However, indeed, it can have some influence. Also, the homogeneous space, all of these are secondary, I think, in my opinion, in the sense that they are very important from the urban perspective. Might be very important, especially when we like to model specific areas. But if you would like to get the minimal representation, I think it's better for us to start with the crude model and then move to this kind of extension, like we're going to show an example. Itzhak, do you have something to extend? To say something extra?
No more question, at least I don't see raised hands, so I continue with extensions, modification, analytics.
Excellent.
Clementine already took us there, so let's continue.
There's just a question, sorry, online from Robin, which was, sorry, have you considered analyzing echo chambers or ghettos in social media? Could such an analysis define an information distance analogous to spatial distance? The question is in the chat if you want to.
Let's delay it, because it's exactly, now it's a story about complications. It's definitely a complication. So maybe then it can be related better.
We'll keep it in mind for the end. Okay, thank you.
I'm trying, it's not that easy to change lines. Yeah, so how many? 5 rhetoric questions that we have to say, okay, let's do that. Why 2 groups? Why the space is homogeneous? Neighborhood size and form are the same for all agents, different group works in different way, identical. Nothing is sacred here. We have to change that. We understand the challenge and the danger. The beauty of the model was very low number of parameters, even if it's in its, I would say, comprehensive form that Erez has presented in the end. We had only 3 parameters, and not all of them were equally important. M was unimportant. That linear growth of utility was not also that important. It didn't matter what is the form of utility function. Just move to the better, despite you will still be unhappy there. So it was very, very qualitative assumptions. Two additional ones, in addition to F, which still remains the leading one. It was very nice for modeling study. All those changes that are marked at this slide will make everything complicated, no doubt. So can we extract some robust knowledge from them? Let's try to answer this also rhetoric question. The first question is, maybe it's worth to avoid all this stuff. It's impossible, regrettably. So the top row is actually three real examples of real residential distributions here in Israel. I don't remember which city is it, but green, you'll not believe, is the color of Islam, and blue is the color of Jewish religion. So these are Jews and Arabs in Israel. And you see that real residential distribution, so the circle denotes a building, it's real data. And the size of the circle is actually the size of the building. So it's definitely something related to segregation, but segregation is essentially more complicated that we seen in those blue, green images 3 or 4 slides ago. So the bottom row is a kind of abstract representation of the top row. So I would say the third pattern, you see my cursor, right? Eric, do you see that laser pointer?
I'm not sure. That's it. Yes, I do. Excellent.
Okay, so I will use it. So you see, we have both segregation and integration, both below and both up at the top row. So these are segregated areas of Jews and Arabs, and you have quite a large aggregated area of the same entities, of the same ethnic groups. So if we believe that local interaction governs in some way a spatial location of the family, it's a household, so we should complicate our model to reflect that in some way. Otherwise, the model does not reflect the entire reality. It's too primitive. We don't want it to be too primitive. So that was the reason to extend the space of parameters. Not that much. We were lucky to do that moderately. So what was the extension? It's presented here. It's 3 parameters instead of 1, actually. The first 2, actually 2 are instead of 1, and 1 is additional, which Schelling and Sakoda didn't think about. So 1 parameter is split. Let us assume that greens or blues have different level of tolerances. You know, living in Israel, that time both of us were in Israel, we knew that the level of tolerance of Jews and Arabs are definitely different in residential sense. So usually that time, it has changed since that. That time, at least in the places that we observed, so Jews didn't like too many Arab neighbors around. And Arabs were much more tolerant. They were attracted by Arabs, but they didn't try that much to avoid Jews. So we took it as, let's say, reality defines that the tolerance level can be different. And the second parameter that we have introduced was actually the ratio of these 2 groups in the area. It also came from the field, from the reality. Let's say I live in Jaffa. In Jaffa, our population is a minority. It's not 50%, it's about, let's say, 30%, 35 now, but it's still a huge population. It's tens of thousands of people who relocate very intensively. So it's not necessarily 50-50. So maybe it has its influence. Okay, it really has. And the most surprising stuff is here. at the very low preferences are sufficient to get quite a strong segregation. And you immediately understand where it comes from. So let's consider a blue minority here. Blue people demand, oops, something jumped on my screen, sorry. Demand only 3 of 24 neighbors, much below 1/3, much below the tipping point that Erez has presented before in 50-50 population case. So only 3 of blues around is enough. But you immediately understand that it brings us to segregation because blues are minority. So to have 3 blues around, they have to be already concentrated. This automatically makes green almost segregated in over the majority of the area. So on the one hand, it's a nice dynamic phenomenon. On the other, great. We have got an explanation of the pattern which is simultaneously aggregated and segregated. Greens are segregated over half of the area. And over the other half of the area, greens and blues are aggregated. They are aggregated, but we see immediately that the density of blues here is in the area which is aggregated is much higher than the overall density in the population. It's not 20%, it's much higher over this aggregated area. So you see, again, a great advantage of the model. You don't have to push something artificial inside. You just vary the parameter in a natural way and you get new and qualitatively different dynamics that you could not observe when it was 50-50. But it was not prescribed from above 50-50. It was just the case someone had investigated and other people didn't think why not to change it. Okay, let's continue. Oops, it's not easy. Dynamic something, right? Yeah, oops. Yep. How to run it?
It's running.
Click. I have to click on it, right? It doesn't. Ah, maybe it's because of my pointer. Where is it? Oh. So this is the same example as it was static in the previous slide, and you see how it goes. So the additional observation, which is important, is that at least in the model, the pattern doesn't remain steady. It varies all the time. So it's more, I would say, physical or mathematical consequence of the model, but it's important for those who study dynamics of spatial pattern. On the one hand, statistical properties of this pattern are very interesting and very special. On the other, the pattern itself varies all the time. And with this fraction of empty spaces, it varies quite quickly. So it's just an observation which shows how the model is rich, how it takes us to very interesting conclusions, and it's still easy. So that's a great advantage of the model. And now, huge jump. We had no time to make a logical path, no time in this lecture, to make a logical path from those yet simple examples to very general ones. So we decided to
We lost.
He jumped to another Zoom.
He disappeared. No, it's still sharing, I think.
Let's keep it.
Let's see if he's
Minute.
okay.
Erez, do you have
Yes,
a way to?
Yes, until he can return. Ah, we lost the
Yeah, the slides as well.
Just a second, maybe I can find a copy. Maybe we'll be back on time. Could give me 2 seconds. I can find the present location that we are in. Yes, we are here. I can maybe share my screen.
And it's not to add pressure, but you're at about 40 minutes. So just to give you
it's
an
good.
idea.
Excellent. Now okay, so in this case, we are investigating different distributions of tolerances, and to see when we can get these realistic patterns. And in this case, by the way, we can find that a very polar distribution, like U-shaped distribution, is the best for the model. Like if many people are highly tolerant and other people are highly intolerant. And here we have to ask ourselves, is it correct? Is it true? And in some cases, you see the limitation of the model. You know, we can get patterns that are correct, but sometimes the distribution of tolerances, of tendencies might be not realistic. And it's not surprising. It's a very simple model. Now, there are many extensions. This is another nice extension, which include adaptation of tolerance. You know, we all the time assume that tolerance is constant and not changing, but maybe tolerance is changing over time. Of course, it's very hard to know how people's tendencies change over time. It's a very complicated phenomenon. But in this case, they actually said, you know what, let's do something simple. If the agent is happy, he becomes more tolerant. If he's unhappy, he becomes more intolerant. In this case, by the way, it's very nice that you can get the same patterns simply by the exposure to other groups, and you get, again, a U-shaped distribution of tolerance. Other extension, of course, can include economic status, you know, because you can't move anywhere. You are constrained also by your wealth. And then you can say, you know, can I know that race is confounded by wealth. So can I put them apart? Can I separate them? And it's very hard to do, but adding this part to this extension of the model makes sense, because now you can actually see when can you decide what is more important, the wealth or really the race or ethnicity. So there are some analytic work around the Schelling model, which yes, please.
I'm back.
Please come in, Benya.
Moment to add the sentence to the previous slide.
Yes.
Please make it back. Yeah. You see what happens. I will just add a couple of sentences to what Erez has said. So whatever you think about the generation of segregation usually comes true. So if it's economic segregation, if your reaction to the neighbors is strong enough, you will get rich on one side and poor on the other side. So again, advantage of Schelling model is that if you don't destroy your model too much, it behaves intuitively. So the question with the Schelling model is not that qualitative, it's more quantitative. What are the parameters that bring you the intuitive results? Are those boundaries in parameter spaces properly located to get that intuitive result? Whether you don't need some very special values of parameters to get the patterns that you expect. And the second question is whether these domains of parameters that produce intuitive results are large enough to make the model robust. Maybe there are very narrow areas of the sets of the parameters that produce your results. It means something is wrong with your model. So this is a kind of very strong educational points that come from Schelling model. So these educational models, let's go to analytical stuff.
Just a second.
People try to prove analytically, physicists
they dare to say that they can prove everything in this world with the proper model, which is analytically formulated. Actually, I would say not that many theoretical models, let's call it theoretical analytical models, bring something new. In this and next slide, I have chosen several of them that are worth reading if you are used enough to read formulas. But let's get back to the previous one. So I'll say that was a paper which changed which was a kind of paradigmatic change. So this paper said that Schelling model actually has two very different phases of dynamics. The first phase is when something similar to segregation is being established. It's actually a very fast stage. It takes not that many iterations. It can take 100 iterations and you have something segregated. And then you have a very long period, it's millions here you see, of segregation, which is never becomes steady. So the physical analogy here is actually a water or mixture of liquids of different colors or whatever. So the boundary can change all the time. So that was an observation. And this paper also proved that the stalled, the frozen state where no one has a place to go is quite typical for Schelling model and should be taken as a special state. So then please go next stage. And one more point I can say with this slide. There is an additional mechanism which can be introduced, which is close to the mechanism of introducing empty spaces. An opportunity, an option to destroy the stalled
Have we lost Itzhak?
It seems.
Let's wait for 2 seconds. Okay.
Yes, if Erez, if you don't mind taking over.
I try to take over here, and indeed, here is a list of papers which take some analytic analysis of the model. Many of them are quite hairy and difficult to understand, really. So if you are very brave or very please take a look at them. Now, when we are talking about the Schelling model, we have to think about so to speak, the Schelling hypothesis. Does it really work this way? Because you can always create a model which might work, but do people really care about the local environment? Or more specifically, do they really care about the ethnic composition of the environment? And it's not clear if the model can answer this question because of so many confounding properties, you know. You don't know if it's really ethnic identity. You don't know actually if there's some other explanation that's explained. Maybe it's the type of houses, maybe it's the size of the apartments, which simply are controlling all what we see. So sometimes you need to go back to the field and see what is going on. So of course, the first step is like we did. We looked at the patterns of segregation and try to understand what we see. We already talked about this, but it's good idea to see that even in Chicago you can see a lot of segregation, but some integration. You can see the diversity map, and interestingly, it's a complicated story because if you have integrated area, it not means that all the groups are integrated. For example, in this area, this is called Uptown of Chicago. You can see that we have many groups, but very few Black. So not everybody actually are participating in the integration. So it's something to remember. It's also very interesting from the point of view of the point of view of studying these areas. This is an example of New York, again, much more diverse, but again, you can see highly integrated area like in Queens. You can see this red patch in Queens, and again, many groups live there together. However, at the same time, not all of groups, again, not enough blacks live there. So it means that even integration itself has diversity. Even diverse area are diverse. And it's something that we need to, at least to remember. Of course, we can also ask people about their tendencies. And for example, this is an example of a study from Detroit, and which asked white and black people how are they willing to live in neighborhoods with certain proportion of other races. Now, the interesting thing to see here is what we already probably knew about minorities in Israel, is that majority group, this in the past, was really willing to live alone, you know, at a very high majority. However, the minority tends to prefer more diverse areas. Now, why does it happen? It can happen maybe because the minority is much more tolerant. Maybe they have to be tolerant because they're a minority, or maybe it's confounded by other factors. For example, it might be that mixed neighborhoods are doing are better neighborhoods in some respects compared to highly segregated neighborhoods, especially when we're talking about minorities. So is it really race? Is it really ethnicity, or is it something else? The only way to learn is to ask people and try really to control for other variables. If we look at some maps again, you can see the same goes here, the complexity. This is Jaffa in Tel Aviv. You can see diversity in the diverse areas. We have areas of Christians and Muslims, an area of Christian, Muslim, and Jewish, an area of mainly of Jewish, and a lot of complications that we can deal with really when we are relaxing the model a bit, even though not everything can be explained so easily, like the Christian and Muslims. It always looks random, you know, so it's not clear if there is a pattern within the Christian and Muslim populations. This is another city in central Israel, Ramle. And here again, we see the same pictures, minority, majority, and integrated area. I must say that in Israel, at least, this pattern only exists in mixed cities, because many cities in Israel tend to be either completely Jewish or completely Arab Palestinians. So you don't see this mix. But when you see the mix, usually for historical reasons, because these are mixed cities, you can see this interesting pattern. This is unlike the US, for example, that most cities are quite diverse, however, not all the neighborhoods are diverse. And this is an example of study done by Shlomit Flint and Benenson, and they try to really characterize.
I can continue actually.
Excellent, please.
Yeah, now I think my internet is restored.
Let's just,
last 5 minutes. Do we have 5 minutes
exactly.
or we do?
3 minutes, let's say.
3 minutes.
Please.
This is a very special example. And its advantage is that you have several groups which have the same and very low economical status living together. These are Haredi people, ultra-Orthodox people in Jerusalem. All of them want to live in the neighborhood which is called Sanhedria. It's an area of about 1 square kilometer. Areas you have to, it's not my presentation, so please next slide, or just push it.
Please, I'm sorry.
Yes, so this is Sanhedria. It's a slope from which you can see the old city, the holy place. So everyone of those religious sects want to live there. Go ahead. Here is, next slide, please.
Mm-hmm.
So this is the history of Sanhedria. And the history of Sanhedria is extremely well described because there is an issue of kosher. So you cannot occupy the apartment if it's not kosher enough. To be kosher, you have to know that it's kosher. You have to know the entire history from the moment the building was established. So you know the dynamics, and every resident in Sanhedria knows all the residents of the same apartment. So Shlomit Flint have hired religious people to come and ask the families, who were your predecessors there? So let's go ahead. So when you have the entire history, Erez, next slide, please.
Yes.
So this is the dynamics. Let's keep where. So these are four major sects, and this, based on that exact description, we could estimate the probability that the apartment will be occupied, the member of one of the sects, depending on the neighborhood. And those sects don't like each other. We don't know much. Then don't get back, please. There is here it's important.
Sorry.
Yeah, and say make it back twice with an arrow, because I want to see. Just push twice the arrow on your arrow on your keyboard. No, on your keyboard. It's a kind of animation on your keyboard.
What do?
On the keyboard,
okay.
push an arrow back. No, back.
Yes.
One.
Back.
Arrow.
Yes.
Yes, and again. Okay. Still, no. Okay, now it's fine. No, Erez.
Yes, this one.
This one. Okay.
Yes, sir. Sorry. Yes.
So you can try to estimate the probability of occupation of one of the sects depending on the neighbors in the building. And we were lucky that this probability depends on the number of neighbors for different groups. And actually, that dependence was only between two groups among four. One group which is called Hasidim, and the other is Sephardim, Sephardic Jews coming from Africa. And Hasidim, those came from Europe. And they didn't like each other. But the Sephardic people were reactive. And it took them in. So now make with the Erez, with an arrow, go ahead. Oh, we don't know. We're not able to estimate, despite quite high number of residents, what is the shape of the dependency. Whether it's a kind of something which depends on that does not, so the people become happy when there are not that many those whom they don't like. We don't know that. But these dependencies, and now go ahead, Erez, please, next, and next again. So these dependencies were sufficient to describe the entrance of Sephardic Jews into the neighborhood. So it's a large neighborhood, about 1,000 families. So it was enough, sufficient to describe the changes. So that was happened. That's something that has happened. The Sephardic Jews entered there, and the rest of them left slowly because of those close to Schelling relationships. So as far as I know, it's the only documented examples of some relation between the residential decision and the state of the neighborhood. And I don't go deeper into this example because there are buildings, there are neighbors in the building, there are neighbors in the closest building, so no time for that. I think we reached the end. Erez, please go ahead.
Yes,
there are more examples which we don't have time to talk about. They don't have those estimates of dependencies. That's the difference. That example in Sanhedrin is the only documented example we knew about. Maybe there are more. So all the rest were like our Jaffa model. It was a kind of assumption that people react to each other because we believe in sharing logics. So the conclusion is not long. So these are our conclusions. For modelers and for urban scientists or social scientists, whoever, who is not just a modeler. So for modeler, it's a very important example. I would say it stands next after two more popular examples which have some relation to urban dynamics. The first one is game of life, and the second one is Ising model from physics. So Schelling is somewhere there. It teaches us a lot. What does it teach us? First of all, it's a real example of complexity. Very simple dynamic phenomena generates very complex dynamics, especially with some extension. Hidden parameters, modelers forget about that. They are critically important as the small probability to move without any reason. This is what makes the system flexible. How to do that? We understand clearly with Schelling model that it's wrong to start with complex description of reality that we translate into the model. It must be simple in the beginning. We have to understand what can come out of that from the basic assumption and only then complicate it. There is plenty of papers that people artificially, not artificially, arbitrarily, sorry, pick some parameters, make some relationships, get some results, and we know that their explanation is wrong because we started properly. We don't spend time to argue with them, but there is plenty of wrong papers about Schelling model. Urban scientists, not that much, not that many advances. Important is that even with the framework of the Schelling model, you can get different explanations of the same phenomena. And the most disappointing, I would say, that if we want to relate the last one, and this is the last claim, if we want to validate the model, the social model, we have to measure the derivatives, how the process varies in time. It's extremely complicated in social science, but until we do that, we cannot be sure that our model relates to reality. It can be just external, a match between patterns. That's it. Thank you very much.
Thank you.
Erez.
Thank you.
Yeah, thank you very much. And I would first like to come back to the question that you heard previously and ask to postpone it a bit. Sorry. Yeah. Have you considered analyzing echo chambers, ghettos in social media? Could such an analysis define an information distance analogous to spatial distance?
Well, I think yes, and I did it myself, but there are extensions, there are Schelling models on a network, and of course you can take it also outside the urban realism. Yes, you can, and I would call it then you're going to see the Schelling mechanism, because even if you work with some social space and people, let's say, choose their friends according to their opinions, then you're going to see again the same segregation pattern, for sure. So just remember that you're going to get the same mechanism. So people might choose people by their opinions, and you're going to get echo chambers simply because you're going to get segregation of opinions. In opinion dynamics, actually, models sometimes do that.
Okay. Then I will rephrase a bit one question we received about the mobility data and validation of Schelling model. I think were very clear at the end that there are lots of wrong studies, let's say, then wrong interpretations of data, etc. And yeah, to broaden a little bit this question, I know there are lots of empirical studies for Schelling model, and in general, would you say they validate the Schelling hypothesis, or it's hard to say in a way?
My opinion is that it's very inconvenient field. You definitely have ethnicity influencing on residential distribution, and you have economic status influencing that, and you have the cost of living or cost of property. So you have additional factors which are not involved. And to validate, you have to measure the derivative. So how people substitute each other. The rate of substitution is low. The highest possible is 7%, 10% per year. And relations between people vary in time. So in 5 years, you consider the same neighbors as positive neighbors, despite that 5 years ago, you didn't like that. So from my point of view, the Schelling model as a model of residential distribution is a kind of abstraction, which is very important for understanding the underlying mechanisms. But to apply it directly, you have to have that very special example of Sanedria or whatever. It's not for real life residential distribution in arbitrarily mixed neighborhood. It's not for that. It's a model which is an idea more than the reality.
I would say you have to focus on your case study. Some populations tend to be, let's say, maybe some Chinatowns, ultra-Orthodox. It might be relevant to use the Schelling model. But the problem is everything is so slow. Everything is so slow and you don't have much data. So validate it. I would say choose at least case studies which you know that are relevant for the Schelling study. So I would say that if you take a complete city, it might be complicated to talk about the Schelling model. But for certain population like Orthodox, or maybe like Arab Jews, or maybe Chinese population in some areas, this actually can be reasonable way to start.
And do you think it would be possible to have some update of Schelling model? It's not only limiting yourself to residential segregation, but also workplace, school segregation, and put all sorts of data, big data, and supercomputers.
It does. Also, I must say that Schelling actually in '69 also had another model, which was the bounded neighborhood model. And actually this model, which you have like took one compartment or two compartments and people living and entering the compartments, is quite relevant also for schools, for example. For example, let's say that you are a black child in a white school. Let's say you have 5% black children. So even if they have a very minor tendency to be together, which is very, very natural, they have to be in the same class, or at least. So again, you see the same processes in other cases, or even like the question we had about opinion dynamics. For sure, if you choose your own friend according to opinions, even if you don't change your opinions, you have a Schelling-like mechanism. So I think it has like many other processes like percolation or transmission. I think sharing model can even be something very fundamental. And if you're a modeler is doing sociology, even if it's not urban dynamics, I think it's a good idea to know the Schelling mechanism.
I've seen the question of Elsa in the chat. So please.
I can ask the question. Yes.
Yeah. Please go ahead.
Right.
It's above my cognition at least. So reading questions from the chat, it destroys.
Yes, of course. Right. So thank you very much for such a nice presentation. So you explained very well all the sensitivity of the model to many of the parameters. Nevertheless, for the evaluation of the model, something that I am very curious about, specifically because of what you were saying at the end and what Clementine was asking, is that we're very much constrained to the granularity of the data that we have. And the measurement of segregation is very much affected to the level of granularity that one is looking at, right? So of course, this is a very difficult question because we're all, trying to really figure out how to deal with that. But because you've been working a lot with this type of models, do you have any insights? Have you gained any insights with respect to what happens to the model as you aggregate one level up or two levels up?
It's not an easy question, at least for me. You have natural hierarchy of neighborhood, building neighbors at the same floor, all this stuff. And people have more than ethnic preferences. They have different kinds of preferences. So I would say that this is not a model question. That's the question of observations. And my friend John Osh in the University of Uppsala likes that multi-level segregation very much. And he has very good residential data, population data in Sweden. They have very high granularity at resolution of 100 meters, several families mostly. So he doesn't get a simple picture. So even in those mixed cities as Malmö, you have all those different patterns as we have presented with areas in Jaffa or Ramle or whatever. You have different patterns. So the only possible explanation for me is the variation of tolerance, which is a personal property. So it's very convenient explanation. It's something unmeasurable. So I say something unmeasurable is responsible for the variety I can explain with this unmeasurable stuff, which I just distribute in population. Problematically for me is that it just cancels my study. Okay, I say that this is the final explanation. I cannot make it more developed. Maybe it's quite possible I'm wrong, and people have to go deeper and try to validate the parameters, estimate, and generate the distribution. I stop at the entrance. I say this is a reality. Okay, that's
but no, Itzhak, I think I want to say that for models of humans, it's quite a lot. It's very hard to say that we have these kind of models which work for every human, for every city. I think the model actually is quite good for modeling people, which are really, really weird creatures and complicated ones.
Clementine, you have a question, please.
Yes, and it's very much of a follow-up of what you were just mentioning, which is, so in this series, we're trying to see like the unforeseen consequences of some model, not only on urban studies, but also on planning and policy and things like this. And following from that discussion, it seems like it's a very interesting model to think about your intuitions about segregation, but it's a terrible model to plan a city or to, however, I'm pretty sure given the notoriety of this model that it's been used, or at least unconsciously in urban planning. What would you say is actually what we can do with this model apart from thinking about it? And do you have examples of policies that have this model in the back of their mind and the consequences it's had on planning and policies?
Only one example. It's Singapore, when they do not allow people of the same ethnic group to populate the building at the percentage which is above the threshold. This is a very strict, and I would say the policy that will be never accepted in any European country, because it's politically extremely incorrect to do that. But I would say that there are no ethnic conflicts in Singapore. So we definitely go beyond the boundaries of modeling in this specific question and my answer. So being all my life politically incorrect and continuing right now that direction, I would say that until we cross the boundary of let's say, commonly acceptable measures, we cannot change the system. You have to make the current state of the metals, it comes out very strongly in transportation. You have to go beyond the boundaries, make something inconvenient for sufficiently high fraction of population. This can change the situation. The steady state is usually not that effective because steady state is usually what's called user equilibrium. Each one varies his or her behavior a little bit to more or less to fit the system. It's not enough. In real social systems, the difference between the distance between the system optimum and user equilibrium is large. And you cannot move the system to the closest to system optimum until you make it inconvenient for many people. The typical inconvenience, which all of you know, is congestion price in transportation. So until you don't introduce congestion price, you will have congestion. The second example is high parking prices or restriction of parking. Let's say you don't have traffic jams in Tokyo because you cannot purchase a car until you have your own parking place. It's extremely inconvenient. It's extremely unequal. But this brings you lack of traffic congestion. So I think it's a very general problem, definitely not for discussion now. So the gap between user equilibrium, which we definitely reach if you follow the rules of being nice, and system optimum. We don't know as a humanity what's better. Why it should be optimum? Why it should be Singapore? There is no answer. And I would say that's the problem of planning.
In the one last minute, I would say that the Schelling model started 1969, and it has some historical context because at 1969, 71, we in the US, we had desegregation attempts. There was the housing rules started, the housing, all the laws of housing came to the US. Anti-discrimination laws started to come in, and Schelling was not, I think, unaware of it. He decided to choose a situation when people move where they want to move, and the bias comes from the people. But you have to remember that sometimes segregation is part of no choice. Some people segregate because of no economic choice. In the US, at least, there's a long history of discrimination. For example, people of certain races were not able to enter different areas. And actually, the pattern we see historically are partly related to this story. The story of segregation is a type of discrimination. So today we talked about segregation as a type of the bias of the individual. But if you would like to talk about social justice, I think other models should be included. For example, a Schelling model of discrimination. However, what we learn about the current model is that maybe even a low level of discrimination would create a high level of segregation. So you need to discriminate only a little bit to create a high impact. So this is like a summary of a social context.
Thank you very much. And I think that's the main appeal of the Schelling model, is that segregation empirically is so multifaceted and complicated, and then we've got a model that's so simple, and I guess the tension comes also from here. I'm very sorry that we have to finish this seminar because we're already over time, but I really want to thank you very much, the both of you, for your contribution, and I want to invite everyone, so yeah, we can have a round of digital applause, and I want to invite everyone, if you want to continue for the next session, to join us again on the 9th of May, another Monday afternoon, to listen to Professor Michael Batty talking about foresters, SimCity and cities as systems. Thank you very much again.
Thank you so much.
Have a good morning, a good afternoon, a good evening.
Thank you.
Thank you. Bye-bye.
Bye.
Bye-bye.